Hello friends, in this video we are going to discuss about Poiseuille's equation for the rate of flow of liquid through a capillary. Okay, and this is my Insta ID. If you want to follow me on Insta, you can follow me Poiseuille LAKHYAJIT. Poiseuille 123. This is my Insta ID. You can follow me on Insta. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. So now let's start. So suppose let us consider this is a capillary tube. Okay, I have considered one portion of that, and now let me consider a cylindrical layer. Okay, this is a cylindrical layer, suppose. Let me consider that way. Okay, so it's the radius of this cylindrical layer is suppose x. Let me consider that way. Okay, that is x, and the radius of this capillary tube is suppose r. Let me take this is r. R is the radius of this capillary. Let me take that way, right? And here you see the velocity of liquid flows through this this tube will be maximum here at the center because of the viscosity. The velocity of the layers of liquid which are close to this surface, that that layer will be minimum. Okay, the layer which is close to the surface or in contact with the surface, that will have minimum velocity because of viscosity. Viscosity is a kind of friction, you can consider friction of fluid. Okay, you may consider that way. So now let me write what I have considered here. Okay, just give me a second. So here you can see what I have considered here. I have considered a layer of liquid coaxial with the capillary tube. That means axis of this capillary and the axis of this layer of liquid that I have considered here with the dotted line, drawn with the dotted line. You can see axis of both this tube and this layer is same. Okay, so coaxial, that's why. And now you see, let me consider one more thing. The length of this tube is suppose L. So I have already mentioned what is the radius of this tube and the radius of this layer and the length of this tube here. Okay, and here you see at each and every point on this of this layer, the velocity of liquid will be the same, that is I have considered v. Okay, I have considered v, but velocity changes when you come from the when you move from the walls to the towards the axis, then velocity changes due to viscosity, right? Okay, because you see, suppose this is the wall of this tube and this is a layer of liquid which is in contact with this wall, and because of viscosity this layer of liquid will be slower than the layer of liquid which is above this layer. Okay, which is above this layer. Okay, so this is the wall, and this layer, black layer, will be slower than the layer which is towards the here you see this is the axis. When it comes towards the axis from the wall, so if you imagine the liquid consists of many layers, okay, then the layers towards the center are moving faster. Okay, that's the thing that I am trying to explain. And the rate of change of velocity with this is suppose let me consider, if you consider this one, suppose this is another layer just above this layer, and the difference in radii of these two layers is suppose dx, then x plus dx will be the radius. In that case, from this layer to this layer, from this layer to this inner layer, when you come from this layer to this layer, then velocity change suppose dv, okay, right? And when there is a change in radius dx, then change in velocity is suppose dv, then we're gonna say this is a velocity gradient. Okay, so hope you have understood this. So that means let me tell you again, let me explain it again. Now here you see at every point the velocity of liquid is suppose v, and I have considered another layer which is just above this layer, and radius is suppose this part is suppose dx, then radius going to be x plus dx, right? And the velocity difference between this layer and this layer is suppose dv. That means velocity at this inner layer is v, then outer layer is suppose v minus dv, because this outer layer will be slower, which is close to the wall, right? So you can consider that way. Then the rate of change of velocity with this distance towards the axis from the wall will be given by, you know, velocity gradient that will be dv by dx, right? Velocity gradient is given by dv by dx, right? So here let me write this one, add one more thing. Let me add one more thing. Just wait. Now you see here velocity decreases, right? Sorry, let me write velocity increases, okay, from the walls of the tube, towards the axis, right? So when you come from this wall towards the axis, okay, then velocity increases, okay, and maximum here at the when you come to axis, this is maximum velocity. All right, hope you have understood this. Now according to Newton's law of viscous fluid, Newton's law of viscous flow, according to Newton's law of viscous flow, the viscous force F is directly proportional to the area of this layer, area of this layer, okay, area of the layer, okay, and F is directly also proportional to gradient of velocity dv dx, right? So let me write these things here, okay. So you see, if you combine these two, you can write F varies as a dv by dx, and when you write equal, there must be a constant, and that constant is nothing but viscosity, okay. That constant is nothing but coefficient of viscosity, not viscosity. So here we are writing negative because this viscous force acting in the direction opposite to the direction of the flow of liquid. So that's why this viscous force F is nothing but minus eta a dv by dx, right? So now let me clean these things, just wait. So here this eta is nothing but coefficient of coefficient of viscosity, and A is the area of the layer of the liquid layer, and dv by dx is velocity gradient. We have already got that, right? So now you see this area that's gonna be equal to, now you see, if you consider this cylinder, this cylindrical layer, coaxial layer, so here we know the curved surface area of a cylinder is 2 pi r into h. Here instead of h we're gonna take L. So if the cylinder is vertical like this and height is h, then we used to write this formula, but now it is horizontal, so we're gonna take the length. And here you see this radius of this layer is x, so that's why 2 pi x L. So instead of 2 pi r into h, this h is replaced by L and small r is replaced by x, right? So that is the area, curved surface area of this cylindrical layer. Okay, so hope you have understood this. So now that's why we can write this formula, this one, in this way. F is equal to minus eta. Instead of A we're gonna write 2 pi 2 pi x into L, then dv by dx. That's what we're gonna have, right? So let me take this as equation number 1. Let me consider this is equation number 1. Now let me copy this equation. Let me go to the next slide. Okay, so here is the equation. Okay, so now you see pressure difference. Just wait, let me copy the diagram as well. So let me take this diagram, and here is the diagram. Okay, this is the length L, right? So here you see the pressure difference, or you can say one more thing, now the flow of liquid is maintained by the forward force due to the difference of pressure. Okay, so if we consider the pressure difference between these two ends is suppose P. Okay, is the pressure difference between the two ends, then what we're gonna add, now let small p is the pressure difference between the two ends of the tube. Okay, of the tube. Now you see, so pressure, we know pressure is equal to force per unit area, that is force by area. So force is equal to pressure into area. Now here you see, here it is pressure is P1, this is pressure is P2, and if the liquid flowing through this direction, flowing through the tube in this direction, then this pressure must be greater, and the pressure difference P1 minus P2 that we have taken P here as I have mentioned, then the net force acting on this the force which is responsible for the flow of liquid, that will given by, as force is equal to pressure into A. So this pressure difference, because force, if the liquid is flowing in this direction, the force due to pressure P1 will be in this direction F, right? And due to P2 will be in this direction, but F1 must be greater than F2, and the net force acting on the liquid, that will be given by that will be given by, you see, that will be given by the pressure difference, that is P into area, that is area of this cross section. Okay, area of this cross section, that is pi x square, right? Pi x square. this P into pi x square, that is pressure difference into the area of cross section of this layer, gives the force that that is responsible for the flow of this liquid layer through this tube. Okay, so hope you have understood this. So that's why what we're gonna get, therefore the force tending to accelerate the cylindrical liquid, therefore the force tending to accelerate the cylindrical liquid layer is pressure difference P into area of this area of cross section of this layer pi x square, and this force must be equal to this one that is obtained in equation number 1, right? So as the velocity of liquid layer is constant, right, velocity of liquid layer is constant. Okay, so velocity will be different for different layer, but this liquid layer at each and every point velocity is fixed. So that's why the accelerating and retarding forces on the layer will be equal. Okay, this is the retarding forces, viscous force, and this is the accelerating force, so both must be equal, right? As the velocity of liquid layer is constant, therefore the retarding force, that is eta 2 pi xl dv by dx, that must be equal to p into pi x square. That's what we should get, right? So hope you have understood this. Now what are the things that you can cancel here? Pi, definitely you can cancel pi, right? Pi cancels, and this x cancels x square, right? So that's why this implies that dv is equal to minus here p and p by 2 eta l into dx. That's what we can write. And one more thing, there should be 1x, right? So here let me write that x here. Okay, that's what we're gonna have. So hope you have understood this. Now you see, if we integrate this, right, if we integrate this, then what we can do here, you see. Now here you see here this case, velocity velocity of liquid at each and every point on this liquid layer, the layer which is dotted with the which is drawn with the dotted line here, you can see at this surface at x is equal to at x is equal to x, that means here, okay, here what we have got here, v is equal to v is the velocity of the liquid at each point on this surface of this liquid layer is v, and here which is the layer which is in contact, that means where x is equal to capital R, here velocity is equal to 0, and velocity is increasing towards the center, right? So hope you have understood. The velocity is increasing from 0 to v. Okay, so hope you have understood this, right? So that's how that's why we're going to integrate this taking the limit at x is equal to x, the velocity is v, right, where at x is equal to r, the velocity is 0. Okay, so if we integrate that way, then let me copy these things and let me go to the next slide. Okay, so here you see So if we integrate this, right, so these terms are these are constants. So here we are integrating from v equal to 0 to v, and x is equal x to x is equal to r. Okay, then what we're gonna have, at x is equal to r, v is equal to 0. So here we should write r here, and this should be x. Okay, so then here v, integration of dv is v, and we are integrating it 0 to v, and if you upper limit, if you put the upper limit and lower limit, then you're gonna get v minus 0, that is equal to v minus p by 2 eta l. Integration of x dx is x square by 2, and here you see the lower limit is r and the upper limit is here x. Okay, so now what you can do, now let us put upper and lower limit. Then what we're gonna have, p 2 eta l by x square by 2 minus r square by 2, and on removing the bracket, then we're gonna get v is equal to, you know, this minus plus, that's gonna be minus minus plus, that's gonna be plus, you know, p 2 pi, sorry, not pi, eta l. If you multiply this minus, then here you're gonna get r square by 2, then minus x square by 2, that's what you're gonna get. And if you take this half common, right, then you're gonna have here r square minus x square, and here this 2 gonna be 4, right? That's what we're gonna get, right? Hope you have understood this. And this gives the velocity of flow. Okay, this gives the velocity of flow, right, at a distance x, okay, from the axis of the tube, from the axis of the tube. Okay, suppose this is equation number 2. Let me write, this is equation number 2. So let me use another color. This is equation number 2. Okay, now you see, let me draw the diagram again. Just wait, let me take a new slide. Okay, so here is the diagram. Okay, and what was the last step we have got? This is the equation number 2. This is the last equation we have got. Now you see, let me consider another layer here. You see, let me consider another layer just above this layer that we have considered earlier. Let me consider another layer. This is another layer. Okay, this is another cylindrical layer. Okay, like this. Okay, and this layer, you know, its radius is x plus dx. Okay, so its radius is x plus dx. This distance is dx, I have considered. Okay, this distance is dx. You can see this distance is supposed dx. If you consider that way, then its radius will be x plus dx. Its radius will be, just wait. Okay, this was the okay, this radius will be x plus dx. Let me consider. Let me write what I have considered here. Okay, just give me a second. So here I have considered another coaxial layer of radius x plus dx. Now you see, and so here you see, this was the initial layer. Suppose, let me draw here. This layer we had here, this one, this is the initial layer, and its radius is x. And the next layer we have considered, now this is, suppose its radius is now x plus dx, right? Now you see, area of this cross section, this one, okay, area between the, you know, two layers, area of cross section between the two layers, this part, So this area will be given by, now you see, if you imagine that if you cut this like this, okay, if you consider this ring, okay, and if you cut it, then it's gonna take the approximately not exactly like this, but almost this kind of shape you're gonna get if you cut it like this, okay. And this part is dx, right? This is dx, and this length is the circumference of this, okay, and that circumference will be 2 pi x, because its radius is x, and this dx is very small length, so we're gonna take 2 pi x only, and 2 pi x into dx, that's gonna give you this area of this rectangular form, okay. So that's why area of cross section, area of cross section of the liquid between the two layers of radius x and x plus dx, okay, is given by a is equal to 2 pi x dx. So let me write it, 2 pi x dx, that's the area, right? Now you see here the velocity of this layer we have considered v, okay, and if you multiply the area of this cross section, okay, then you're gonna get the volume of this liquid through this cross section, that means through between the two layers, volume of liquid per second, that's what you're gonna have. So let me show you why. Because you see, velocity is nothing but displacement by time, right? So if you multiply velocity, suppose displacement by time is means displacement, that is the length covered by this liquid in 1 second per second, this must suppose, and if you multiply this area with velocity v, which is nothing but this area is suppose a, then va gonna give you this volume of liquid in 1 second, right? Because v means the displacement, this length, that means travel by this liquid in 1 second, so displacement by time, and this displacement into a, that's gonna give you the volume, right, per unit time, okay. That's what we're gonna have. Hope you have understood this now. But in this case, so we need to take the volume between these two layers. So here, instead of taking this cross section, we're gonna take the area of this part only, right? So hope you have understood this. So that's gonna therefore the volume of liquid through these two layers flows through these two layers per second, let it be dv, that gonna give you that will be given by v into this area 2 pi x dx, right? That's what we have got, right? Now you see this V is equal to this one. So let me use this equation, equation number 2. Here we're gonna get, so instead of V we're gonna write, okay, sorry, we're gonna write here P by 4 eta L into capital R square minus X square. Then here we have 2 pi X dx. That's what we have got. So using equation number 2, so now let me copy this and let me go to a new slide. Okay. So this is the new slide. Okay, now you see this is the volume of liquid passed through the two layers we have considered. This is the tube, this was the tube, suppose this is the capillary tube, and we have considered two layers like this, right? Two coaxial layers, cylindrical layers like this. Okay, and here velocity we have considered v, right? And now you see, if you want to find the volume of liquid passing through this tube, okay, total volume of liquid passing through this tube per second, okay, now we are getting the volume of liquid passing through this layer, between these two layers per second. Okay, so in order to get the total volume per second, you have to integrate it from x is equal to 0 to x is equal to r, because the radius is capital R here, right? So that's why, therefore total volume of liquid, okay, total volume of liquid flowing per second through the capillary tube is, V is equal to P 4 eta L and R square minus X square, if you integrate it, into 2 pi X dx. So here this 2 pi can be taken outside because it is constant, right? And so here P 4 pi, sorry, not pi, eta L 2 pi integration. Now this multiply this x with this, then R square x minus x cube dx. That's what we're gonna have. This 2 cancels, this 4 2 gives 2, so that's why P by 2 eta L, then pi also there. Now integrating it from x is equal to 0 to r, right? 0 to r. So if you integrate this x dx, then you're gonna get x square by 2, right? Then minus, if you integrate this x cube dx, then you're gonna get x to the power 4 by 4. So here we are integrating it from 0 to r, right? So if we do so, then what we're gonna get, pi p 2 eta L. So here if you put here r, then it's gonna be r square r to the power 4 by 2 minus 0. If you put 0, then you're gonna get 0. Then if you put r here again, then that's gonna be r to the power 4 by 4. That's what we're gonna have. So now V is equal to, now if you take the LCM, okay, then pi p by 2 eta L, on taking LCM, what you're gonna have, you're gonna have here 4 to r to the power 4 minus r to the power 4, and that's gonna give you V is equal to pi p and r to the power 4 by 2 4s are 8, right? 2 4s are 8 eta L. So let me write this. So this is the equation, required equation, Poiseuille's equation. right? What was the equation? Let me write it properly, just wait, give me a second. So what we have got V is equal to pi p 8 eta L, and here r to the power 4. Okay, that's what we have got. So this is the Poiseuille's equation, right? This is the Poiseuille's equation.